Pointers are the single most feared topic in programming. They're the reason C has its reputation, the reason segfault is a word developers say with a shudder, and the reason languages like Java and Python were invented to hide them from you. But here's the thing. Pointers are also the closest your code ever gets to what the machine is actually doing. And today we're going to make them completely concrete by printing real memory addresses at every single step, with GCC compiling real C on this machine. We'll mutate variables through pointers, decode pointer arithmetic, allocate heap memory by hand, and at the end, we will crash a process on purpose, live. Let's demystify this thing forever. One mental model powers this entire video, so let's install it first. Your process's memory is one gigantic street of numbered houses. Every house is one byte, and every house has an address, just a number. A variable is a few consecutive houses with a name. An int is 4 houses. That's it. And a pointer? A pointer is a variable whose value is an address. A piece of paper with a house number written on it. That's the entire concept. Everything that follows, the ampersands, the stars, malloc, the crash, is just this one idea wearing different outfits. Paper with an address on it. One honest footnote before we start printing addresses. The numbers we'll see are virtual addresses, not physical locations on the RAM sticks. The operating system gives every process its own private imaginary street and translates to real hardware behind the scenes. That's why two programs can both think they own address 1000 and why one process can't read another's memory. For everything we do today, the model is identical. It just means the street is per process and the OS is the landlord. Remember the landlord, he shows up again at the end. Let's meet the two operators that scare everyone, ampersand and star. File 1, address.c. An int, x, holding 42. And then the line that makes pointers real. Int star p equals ampersand x. Ampersand means, give me the address of. So p now holds the house number where x lives. Now let's print everything there is to print. The value of x. The address of x, using the %p format. The value of p, which should be that same address. And star p, which means, go to the address written on the paper and read what's there. Dereferencing. And then the punchline, star p equals 99. Right through the pointer, and then print x again. Compile with GCC, and run. Look at this output, it's the whole story. X is 42. Its address is this big hex number, a real location in this process's memory, right now. P's value is the exact same number. The paper has the house number on it. Star p reads 42 through the pointer. And then, the magic. We never touched x. We wrote 99 through p. And x is 99. Two variables, one memory location. That's aliasing, and it's the superpower and the danger of C in one sentence. Read the declaration as a sentence and it all parses. Int star p means, p is a thing that, when dereferenced with star, yields an int. Ampersand takes you from a variable to its address. Star takes you from an address back to the variable. They're inverses. That's the entire grammar of pointers. Now let's look at how memory is actually laid out, with an array. For ints, 10, 20, 30, 40. I'll print size of int, and then each element's value, and, crucially, each element's address. And then the experiment that explains a dozen C idioms at once. I assign the array to a pointer, no ampersand needed. Arrays decay into pointers to their first element. Then I print star p, star of p plus 2, and p bracket 2. Run it, and read those addresses closely. 850, 854, 858, 85C. Each element is exactly 4 bytes after the previous one, because ints are 4 bytes, and array elements are packed shoulder to shoulder, contiguous houses on the street. No gaps, no overhead, no per element headers like a Python list. This is why arrays are fast, and why CPU caches love them. And the pointer arithmetic. P plus 2 gave us 30, the third element. Notice it did not add 2 bytes to the address. It added 2 ints, 8 bytes, because pointer arithmetic automatically scales by the size of the type. And the last line is my favorite fact in all of C. P bracket 2 is defined as star of P plus 2. The square bracket syntax you've used your entire life is, and always has been, pointer arithmetic in a costume. Arrays and pointers aren't cousins in C. They're the same machinery. Quick experiment while we're here, because it answers a question that confuses everyone. How big is a pointer itself? Let me print size of for 3 data types, and for pointers to those same 3 types. The data types vary. 1 byte, for bytes, 8 bytes. But the pointers? 8, 8, 8. Every pointer is the same size, because a pointer is always just an address. And on a 64-bit machine, addresses are 64 bits, 8 bytes, no matter what they point at. A pointer to a char and a pointer to a million-element struct are the same size, 1 house number each. The type only matters for what happens when you dereference, and how far arithmetic jumps. Time for the classic interview question that pointers exist to solve. Write a function that swaps 2 variables. Here's the version every beginner writes first. Broken swap takes A and B, uses a temp, swaps them. Looks perfect. It compiles. It's completely useless, and I want you to see why with your own eyes. And here's the real version. The only difference, it takes int star A and int star B addresses, and every access goes through a star. Read through the pointer, write through the pointer. And in main, we call broken swap with x and y, then real swap with $x and $y, printing after each. Run it. After broken swap, x is still 1, y is still 2. Nothing happened. Because C passes arguments by value. Broken swap received photocopies of x and y, swapped the photocopies diligently, and threw them away when it returned. The originals never knew. After real swap, x is 2, y is 1. It worked, because we didn't send copies of the values, we sent the addresses. The function reached back into main's memory and swapped the actual houses. When you pass a pointer, you're not passing the data, you're passing directions to the data. Now, where do all these variables actually live? 2 neighborhoods, and the difference between them runs the entire software world. The stack is where local variables live. Every function call gets a frame, pushed on entry, and this is the crucial part, destroyed on return. Automatic, fast, and ruthless. Which creates a problem. What if a function wants to create something that outlives it? Returning the address of a local is returning the keys to a demolished house. That's where the heap comes in, a big open region where you rent memory explicitly, with malloc, and it stays yours until you free it. No automatic cleanup. Full control, full responsibility. Let's use it. Make counter asks malloc for size of int bytes, 4, on the heap. Malloc returns, what else a pointer. We initialize it to 0 through the star, and return the pointer. Returning the address of a local would be a bug. Returning a heap address is perfectly legal. The heap doesn't care about function boundaries. In main, we get the counter, increment it 3 times through the pointer, print it, and then, the sacred ritual, free it. Every malloc must eventually meet its free. Run it. Counter is 3, living at a heap address, and freed cleanly. And notice that heap address starts with a completely different prefix than the stack addresses we saw earlier. Different neighborhood, literally. Now, forget the free, and you have a memory leak, rented houses never returned, until the process bloats and dies. Free it twice, or use it after freeing, and you get corruption bugs that security researchers build entire careers on. Every use after free exploit you've read about in ACVE is exactly this, a pointer to a demolished house, still being used. Before we leave the stack and heap, let me actually commit the crime I keep warning about, returning the address of a local. Here's bad idea. A local int, value 7, living in bad idea's stack frame, and we return its address. The frame gets demolished the instant the function returns, so this pointer is born pointing at rubble. A dangling pointer. And watch what happens when I compile with -w all, warnings on. GCC catches it. Warning, function returns address of local variable, with the exact line and a little caret pointing at the crime scene. Modern compilers know decades of pointer disasters by heart, and -w all is you asking them to share. There is no excuse for compiling C without it. Free code review from a reviewer who has seen every bug since 1972. Quick tour of one more place: pointers hide in plain sight, strings. Because in C, there is no string type. A string is an array of chars, with a secret at the end. Here's the word hello, and I'm printing two different sizes of it. String length says 5. Size of says 6. Where's the extra byte? The loop reveals it. H, E, L, L, O, and then, at index 5, a character whose numeric value is 0. The null terminator. Every string literal in C carries this invisible final byte, and it's the only way anyone knows where the string ends. String length is literally a pointer walking forward counting until it steps on the 0. And I'll do exactly that walk myself, a char pointer starting at word, printing characters until $p is the null byte. And it prints hello, one character at a time, writing a bare pointer. Now you also know why buffer overflows exist. If that terminating 0 ever goes missing, overwritten by 1 byte too many, every function that walks the string just keeps walking, straight through whatever memory comes next. Decades of security disasters, from the Morris worm onward, live in that one missing byte. And now, the moment I promised. We're going to crash. On purpose. Because you should see what the famous crash actually looks like in a controlled experiment before it ever ambushes you in real work. The setup is 2 lines. A pointer, p, initialized to null, address 0, the universal value for points at nothing. And then, write 42 through it. Compile, run. The first print appears, and then, silence. No second print. The process is just gone. Let's ask the shell for the exit code. -10737411819. That number is hex C00000005. Windows speak for access violation. On Linux, you'd see the word segmentation fault. Same event, same cause. Here's what actually happened, and it's genuinely good news. The operating system keeps a map of which memory pages your process may touch. Address 0 is deliberately never on that map. The CPU tried to write, the hardware flagged it, and the OS killed the process on the spot. The seg fault isn't the disaster. The seg fault is the safety net catching a disaster. The truly frightening pointer bugs are the ones that write to memory you do own. Wrong place. No crash. Just silently corrupted data 3 functions away from the actual bug. Which is why real C work leans on tooling. We already saw -w all catch a dangling pointer at compile time. At runtime, the big gun is address sanitizer. -f sanitize equals address on GCC and Clang, which instruments every memory access and reports leaks, overflows, and use after free with full stack traces the moment they happen, instead of 3 functions later. On Linux, there's also Valgrind. If you write C beyond toy programs, these tools aren't optional extras. They're the difference between debugging in minutes and debugging for days. So let's put pointers in their historical seat, because every language you use is a response to what we just did. Java, Python, JavaScript, C#, they took pointers away, wrapped every object in a managed reference, and hired a garbage collector to do all the freeing. Safe, productive, and you pay in runtime overhead and lost control. Go kept pointers. You'll see ampersands and stars there, but banned the arithmetic and added a garbage collector, a curated middle ground. And Rust made the boldest move. It kept full control and 0 overhead, but built a compile time system, ownership and borrowing, that proves your pointer use is safe before the program is allowed to exist. Use after free, double free, data races, rejected at compile time. Every one of those designs is answering the exact bugs we met today: leaks, dangling pointers, and the null right. You now speak the problem all of them are solving. And yet, C is not going anywhere. The Linux kernel, most of Windows, your database engine, the Python interpreter itself, Git, curl, SQLite, the firmware in your keyboard, all C. When you need to know exactly where every byte lives, and exactly when every instruction runs. This level of control is the whole point. The languages above it aren't replacements. They're floors built on top of it. Learning pointers isn't retro computing. It's learning the ground floor of the building you already live in. Let's fold the street map back up. Memory is numbered houses, and a pointer is paper with a house number. Ampersand gets an address, star follows 1, and writing through a pointer changes the original, which is what makes real swap work and photocopy swap useless. Arrays are contiguous houses, and bracket indexing is pointer arithmetic in disguise. The stack demolishes on return, the heap rents until you free, and forgetting that contract gives you leaks and use after free. Strings are char arrays ending in a hidden 0. And the segfault is the OS's safety net, not the disaster itself. Pointers aren't dark magic. They're addresses, and now you've read them off the screen yourself. Every file today was a dozen lines, and typing them yourself, watching your own addresses come out, is worth 10 textbook chapters. If this finally made pointers click, a like genuinely helps the channel, and subscribe for more deep dives. Next time, we're jumping to the opposite end of concurrency, goes routines and channels, with live race conditions and their fixes. See you there.